Hi everyone. So this is Lakshmi here going to demonstrate the implementation of CE Amplifier using TinkerCAD. So this is a site where you can simply log in with your mail ID. The use of this TinkerCAD is you can design any 3D architectures or shapes followed by circuits. You can also even generate the codes. So this video demonstrates the implementation of CE Amplifier using the breadboard. So the right hand side, by clicking this option, we'll be able to list out all the components available for our implementation. First, we are going to paste a breadboard. And to start with, this is the CE amplifier circuit which I am going to implement now. So the values of the biasing resistors are R1 equal to 280.6K, R2 equal to 52.8K, RC is 4.8K, RE is 1.2K, value of C1 is 0.17 microfarad, C out is 0.33 microfarad, and CE is 1.33 microfarad. So all these values are obtained based on the design specifications. So now let us start connecting these components one by one into the breadboard. First, start with the transistor. We have two options, NPN transistor as well as PNP transistor. So here we cannot use the different specification transistors. So now I'm going to use NPN transistor. So by simply placing the mouse, here it displays the terminals. So this is a collector terminal, base terminal, and emitter terminal. So coming to the circuit here, what you have is the R1 first connected between the base and the supply. So identify the resistor. A resistor is placed and you need to name that resistor as R1. The value of R1 is 280.6 kilo ohms. It is already in kilo ohms. You see here, as you enter the value of the resistor, the color coding of the resistor also changes. So depending upon our convenience, we can also rotate this component for a better connection. So this R1 must be connected between the base and the supply. Next, we need to have one more resistor connected between the base and the ground. So we choose one more resistor and we rotate it the value here you can change the name be R2. Value of R2 is 52.8 kilo ohms. So we use another resistor to be connected between the emitter and the ground. You can change the name to be RE. The value is 1.2 kilo ohms. So one end of this RE to be connected to ground, the other end of RE be connected to the emitter. So next we have one more resistor. See, collector resistor. We name this to be RC. Value of RC is 4.8 kilo ohms. And we can rotate this. We can place between the collector and the supply. So now we need to connect the capacitors. So you can use either a polarized capacitor or a simple dielectric capacitor. So here I choose the dielectric capacitor, C1. I name it as C1. The value is 0.17 microfarad. So here I change the option to micro, and this capacitor, you see the circuit, this capacitor must be connected between the input end and the base. So, excuse me. So this is a capacitor. This end must be connected to the base. And this is the terminal where we need to connect the function generator. So let us come to that finally. We need to connect two more capacitors. So let this be the emitter or a bypass capacitor CE. The value of the CE is 1.33 microfarad, and one end is connected to the emitter, the other end is to be connected to ground. So now we need to connect one more capacitor, that is at the collector. So let us connect this capacitor positive end to the collector, and negative end, this is the terminal where you need to connect the CRO. So this is the input capacitor, this is the output capacitor. Of course, you need to change the value of this output capacitor, 0.33 microfarad. C2. This is C1. This is C2. This is CE. So now we will complete the VCC and ground connection. So this end, this is actually R1. R1 and RC must be shorted and to be connected to the VCC. So I take these two ends and I connect it to VCC. So this is my VCC line. I've shorted R1 and RC and connected to the VCC line. And I'm going to now give the ground connection. So this is actually your R2. One end of R2 is connected to the base, the other end of R2 to be connected to ground. So we have completed all the connections. Only thing is left out is to connect the power supply, to connect the function generator, and also the oscilloscope in order to observe the output. First, we will take the power supply. We have power supply. I can drag it here and keep it. So now I can fix the voltage and current level of this power supply. So the voltage to be given is 12 volt. The name of the supply is VCC. The voltage you are going to fix is 12 volt. The current will be 2 amps. So here this power supply has positive terminal as well as negative terminal. The positive terminal will be connected to this VCC pole and the negative end to be connected to the ground. So we have one convenience here. All these connections you can represent in different colors based on maybe VCC or ground. You can allocate different colors be for VCC and ground as well as intermediate connections in order to differentiate. So now I've selected this wire and I choose red color because it's positive, and I'm going to select this wire and I'm going to choose black. So this is the connection of power supply to the circuit. Next comes the function generator. We have the function generator. So this is what the specifications of the function generator. Parameters you can set is, of course, the name of the function generator. You can assign it as input, Vin, and the frequency may be taken as 1000 hertz. Amplitude, since this is a CE amplifier, I am going to fix it to 0.1 volt with 0 DC offset, and the function we are going to choose is a sinusoidal function. So with this we have specified the parameters of the input signal. Now we need to connect this input to the circuit. So as per the circuit, we need to connect the input to this capacitor C1, and we need to connect the CRO to this capacitor C2, whose value is 0.33 microfarad. So this end is positive. I am going to connect it to C1, and this end is negative. I am going to connect it to the ground. So we can also change the colors. This may be red, this may be black. So we have completed connecting the function generator to the input. Next comes the CRO to be fixed. So if you take the specification of the CRO to be given, the name will be out, and we can fix the time per division to 1 millisecond because we have given the input frequency to be 1000 hertz. So its corresponding time period is 1 millisecond. Why do we give this 1 millisecond is only then you will be able to observe the sinusoidal output with the free time period of 1 millisecond. So here again we have positive and negative terminals, wires. So positive to be connected to this end of capacitor, and of course negative we can connect it to ground here. For our convenience we can change the color, positive as red, and negative probe as black. So that is the end of giving the connections. So now we will start simulating this circuit. So before that, we can just check it out whether all the connections are given as per the circuit diagram. Yes. So once the circuit is given connection, then you can start simulating the circuit. See here the parameter, input parameters, 100 millivolt, 1 kilohertz frequency. We are running the output of the circuit. The power supply that we have given is 12 volt. So we shall wait till the supply voltage reaches 12 volt. Then we will see the procedure to note down the reading from the CRO or the oscilloscope. Yes. So now we have seen that the supply voltage reaches 12 volt. The input parameters are stable. See here you are able to get the sinusoidal waveform. Now let me zoom this oscilloscope in order to explain the procedure to take the readings from the oscilloscope. See here the time division is total from this end to this end. It is going to be 10 milliseconds. So that means each small division it represents 1 milliseconds. So likewise, if you take the vertical axis, it is 40 volt. So that means each small division. See, this half is going to be 20 volt. This half is going to be 20 volt. That means each small division is going to be 4 volt. Okay. See here, almost this changes. Now you can measure. It's almost equal to one small division that represents 4 volt. sorry, I think, yeah, 4 volt. So from this end to this end, it's going to be 40. So half of this vertical axis is going to be 20 volt. So within that, this small division represents 4 volt. So we have got the output 4 volt. So remember, this is for the input 100 millivolt 1 kilohertz. Can stop simulating now. If you want, you can observe the next reading by assigning the frequency to be 2000, that is 2 kilohertz. You can check what the reading is. So just change the frequency here, again start simulating. Yes, now the supply is stable. It has reached maximum 12 volt. Now we can zoom this oscilloscope and see the changes in the output. Yes. Yeah, again, there is no change in this maximum volt per division. It's again going to be 4 volt each small division. So now it has one division plus maybe 4 volt, again 3 volt, 4 plus 3 maybe 7 volt. So this is the reading for 2 kilohertz with the same input 100 millivolt. So now by changing the frequency in the function generator, you need to observe the output voltage and tabulate it. So once this tabulation is over, you can draw the frequency response. The frequency response is given by the graph drawn between the frequency and the gain. The gain is given to be the ratio of output voltage to that of input voltage, or in decibels it is given by 20 log of V naught by Vn. So thereby we can complete drawing the frequency response as well as calculating the bandwidth of this CE amplifier.